So we start our last talk today by A.G.Khovanskii from the University of Toronto. He will speak about Newton polyhedra and affine algebraic varieties.
Okay. Can you hear me? Hello?
Hear you well. Yes.
Okay. So first of all, happy birthday to Sabir. We got acquainted with Sabir more than half century ago. Both of us were participants of Arnold seminar at Moscow State University. But of course, I heard about Sabir much earlier, when he was just a schoolboy. I attended a seminar at Moscow State University, which was his supervisor was Anatoly Kotov, and Anatoly Kotov was very proud that he had a very gifted schoolboy in his mathematical circle, Sabir, and he loved to talk about his achievements. Today I will talk about subject which was started 50 years ago at 1975 by Arnold and Kushnerenko. And my talk will be very, very related with the very first result of Kushnerenko. The problem is as follows. Assume that you have system of k equations, k polynomial equations in C2 n with given Newton polyhedra. Well, it's not Laurent polynomial, but honest polynomial. And they are not in torus, but in affine space. And the question is as follows. How many irreducible components of different dimensions has the set of solutions of this system? This is first question. And the second question is, well, what is the multiplicity of irreducible components, of such irreducible components? Today I will present complete solution of first part of the question, how many irreducible components of different dimensions has this variety, and partial solution of that problem for multiplicity. I will explain how to find multiplicity of orbits of codimension n minus k. K is a number of equations, n is dimension of space. So this is what I will be talking about today. Well, particular case of that problem. Assume that number of equations is equal to n equations and n unknowns in Cn. So first question is as follows. How many isolated solutions has this variety and of given multiplicity? Unlike the case when all equations are in torus, multiplicity could be just an arbitrary number, and dimension of components also can be arbitrary. So I will present solution of the problem. So how many isolated solutions of different multiplicities has generic system of n equations and n unknowns with given Newton polyhedra? Of course, this problem, this question and its solution can be generalized to arbitrary toric varieties. So assume that we have arbitrary, well, beta smooth toric variety, and assume that we have several invariant line bundles over it. And assume that at each line bundle, we consider invariant finite dimensional space of sections with given Newton polyhedra. So we are given several line bundles and 7 Newton polyhedra of sections of corresponding line bundles. And the question is the same. We consider variety defined by these sections. And the question is how many isolated components has this variety, and what is the variety of, what is the multiplicity of isolated, of irreducible component of a good dimension. Good dimension is dimension which is equal to, whose codimension is equal to number of equations in toric space. Okay, so I will talk basically about space, about this problem in C to the n. But arguments in general case are just very similar or maybe just the same. Of course, I will consider C to the n as a toric variety. C to the n is equipped with standard action of torus and is split into orbits of different dimensions. Such orbits are in one-to-one correspondence with coordinate subspaces. It is a Zariski open set in each coordinate subspace, which is a subspace without collection of points at which sum of coordinates, at which all coordinates, we eliminate coordinates at which all points at which all coordinates vanish. Okay, so consider one orbit in C to the n, or if you wish, one coordinate subspace, more or less the same thing. And with this coordinate subspace, one can associate its own toric variety, which consists of this orbit and all other orbits whose closure contains orbit O. Or if you wish, it deals with coordinate subspaces which contains our chosen coordinate subspace. I will denote this affine space as VO. O is a notation for orbit, and V is just, toric variety. Okay, so we have system of equations in C to the n, and some equations can be identically equal to 0 at our orbit, and some not. So we split our system of equations into two parts. Equations which are identically equal to 0 at the orbit. I will denote the subsystem as one or VO and with subindex 0, and complementary system which consists of equations which are not identically equal to 0 as this orbit. So the first question is as follows: Is our orbit an isolated component of the variety defined by first collection of equations? So we consider equations such that all of them are vanishing at the orbit. It could happen that orbit is a component of variety defined by this equation, but it could be that it is not an orbit. So first question is when it is an orbit, when it is an isolated component, sorry. And the answer is as follows. Let us say that orbit is marked for the system if the following is true. If the following is true, let us consider any bigger coordinate subspace which contains our chosen coordinate space, and assume that our coordinate subspace has codimension m in this new subspace. So let us say that orbit is marked for our system if at least m equations from our system do not identically vanish at this bigger space. So for each bigger space, we consider all equations which vanish on orbit, and I want at least m of them not be identically equal to 0, where m is a codimension of our chosen space in the coordinate space we are talking about. So if this condition holds, then we will say that the orbit is that the orbit is marked by our system. And one can prove the following theorem. Our orbit is isolated is a irreducible component of the system if and only if it is marked for subsystem of equations which identically equal to zero at the orbit. If this condition, if condition I just defined is not satisfied, then O will just belong to a closure of variety defined by our subsystem. So it could not be isolated, it could not be a reducible component. And otherwise it is a reducible component. So we have this notion of marked orbit for system, and this notion will be, of course, very important. And now, well, if we have isolated component, it has some multiplicity in our subsystem. I will denote this multiplicity as mu at O. Multiplicity of orbit O is mu at O, multiplicity for subsystem of equations which identically equals to zero at the orbit. Okay, but now let us include other equations from the system which are not identically equal to zero at the orbit. I would denote this subsystem as just a system with index O, where O is orbit. This system defined some subvariety in this orbit. Of course, as always, I will assume that this subsystem is generic for the collection of the Newton polyhedra. So we split our system into parts. First part consists of equations which identically equal to zero at O, and second part defines some subvariety at O. This subvariety is absolutely not important for us if our orbit is not marked for the system. But if it is marked for the system, so all components of a subvariety in orbit defined by that subsystem will be components of the original variety. And each component of the original variety look like that. So if we want to describe all possible reducible components of our variety, we have to consider different orbits. And for different orbits, we have two questions. Question number one, is it marked or not? If it is marked, if it is not marked, just forget about it. But if it is marked, then at this system, at this orbit, we have its own variety defined by its own system of equations and torus. And one can ask about isolated components of this variety. And they are important for us because they will be exactly isolated components of our variety, of our general variety. Yeah, and it turns out that multiplicity of such orbits, of such components in the ambient variety is equal to mu at O. It's equal to multiplicity of the orbit. So basically our variety splits into orbits. Some of them are marked. This marked orbit has multiplicity, and we consider components of our variety as this orbit, and they will be components of our variety in ambient variety with multiplicity mu. So we have here two questions. Question number one, how to describe irreducible components of subvariety in torus defined by generic system of equations with given Newton polyhedra. Well, I published complete solution of that problem about 10 years ago. So the answer is known, it is simple, and it turns out that all this variety, all this such subvariety, all of them have the same dimension, and more or less, and even more, all of them have the same discrete invariance. The point is that each such component can be in its turn can be defined as a set of solutions of non-degenerate of auxiliary non-degenerate system in auxiliary torus, and this system will have the same collection of Newton polyhedra. So via Newton polyhedra theory, we can compute all discrete invariants of such components, and they are the same for 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 different components, they are the same. But the following question was not answered yet. What is this multiplicity mu? If we will know this multiplicity mu, we will get complete answer on that question. I don't know this answer for system for arbitrary orbit. I know it only for orbits whose codimension is equal to number of equations in the system. This question can be reduced to the following question. Assume that we have system of equations in C to the n with given Newton polyhedra, which has isolated zero at origin. What is the multiplicity of this solution? This question was suggested by Arnold, and was considered first by Anatoly Kushterienko and David Bernstein, and half-century ago, they present explicit formula under assumptions that Newton polyhedra of each equation touches all coordinate subspaces. Under this condition, we know explicit formula, but sometimes even very simple equations do have precise multiplicity at the origin, but the Newton polyhedra do not touch coordinate spaces. Well, maybe the simplest example is as follows. Consider plane with two coordinates x and y and couple of equations. X to n is equal to 0 and y to k is equal to 0. Of course, 0 is a solution of the system of multiplicity k to the n. But of course, diagrams are kind of very poor. Each diagram consists of only one point. And of course, they don't touch both of coordinate lines. So, and this question, how to define this multiplicity, will be main question for my talk. So first of all, first statement is that question out of multiplicity of each orbit can be reduced to the case when orbit has dimension 0. One can do it as follows. So we have some coordinate subspace and collection of equations which identically equal to 0 the subspace. Well, take the Newton polyhedra and project them to the complementary subspace in the composition of real space into subspaces. Subspace corresponding to chosen coordinate subspace and complementary subspace. So we project Newton polyhedra to the complementary subspace. And we will get collection of Newton polyhedra in this smaller subspace. And now one can prove the following theorem. If we will consider in this space of smaller dimension system of equations whose Newton polyhedra are projections of Newton polyhedra we had before, and if we will compute multiplicity for this zero solution, it will be equal to multiplicity of the orbit. So indeed, the main question reduced to the case when we have just isolated solution of system of equations and equations and unknowns in C to the n. Sorry, my vision is very poor and I'm not sure what is on my slides. Would you please help me? What this slide is about?
First formula from
It's called first formula for multiplicity.
Yes, thank you. And
notation, definition.
yeah, so so I am using usual notations. These notations are as follows. So first of all, we consider all polyhedra belong to positive octant because they are Newton polyhedra of polynomials, not of Laurent polynomials. This is first thing. Second thing is that for each covector psi, we have a certain phase in Newton polyhedra. I denote it by delta 2 psi. Delta with psi with the upper index psi. This is first thing. And I will denote by h delta. I will denote support function of Newton polyhedra. Okay, so I will say that we have complete collection of Newton polyhedra if we have exactly n Newton polyhedra in n-dimensional octant. And now I'm going to give this first definition. First definition is non-symmetric local covolume of given n polyhedra. So if you have collection of polyhedra, of course you have symmetric formula for its mixed volume, and you also have non-symmetric formula. This non-symmetric formula is non-symmetric only very slightly. Only one polyhedron plays special role. It turns out that there is a non-symmetric formula for this for number of for multiplicity of isolated solution, which is very strongly non-symmetric. It depends on ordering of all systems. Not only one of them is chosen, but ordering of all Newton polyhedra is important. So we have n tuples of Newton polyhedra, which is just ordered collection of Newton polyhedra, and in this first definition, important role play the last polyhedron. So what we do, we consider, so this formula is a sum over all n minus one dimensional faces of the first n minus one polyhedra, and I want the spaces normal to the spaces out of normal of these faces look to origin. Meaning is that we consider covector psi, which has strictly positive coordinates. So for each covector psi, which has all strictly positive coordinate, we cook this collection of faces. And we consider its n minus one dimensional usual mixed volume, n minus one dimensional mixed volume, and we multiply it by value of support function as this vector psi of the last polyhedron. So in this definition, there is not n polyhedra, but k polyhedra, and I wrote this formula for n equal to k, because all different k's will a little bit later will involve in this more complicated formula. Okay. Now, yes, this is the definition for local mixed volume in the case when when the dimension k is bigger than 1. If it is equal to 1, this first term makes no sense. Yeah, and of course, summation is taking not over all psi, but over primitive integral vectors. And it turns out that the sum contains only finitely many terms. For generic primitive psi, this term will be equal to 0. Only for finitely many of them, it is not equal to 0. So this formula makes sense. So what to do if k is equal to 1? This term will kind of disappear. And if k is equal to 1, we have just segment in one-dimensional space, and its local covolume will be just this term. We put this we consider this term as one. Yeah, so this is a definition of a local covolume for complete k tuples of polyhedra in k-dimensional space. Again, here ordering is very important. Who is the last? And ordering is even much more important for the next definition. I'm going to consider multipositive octants and multituples of polyhedra. So assume that we have decomposition of our space into direct sum of coordinate subspaces. So if we have a partition of set of indexes, then with this partition, we can associate decomposition of our space into direct sum. And correspondingly, positive octant also will be direct sum of positive octants in this space. Such guy I will call multipositive octant. So multipositive octant is a decomposition of our original octant into direct sum of this complementary, of this positive octant in different spaces. And now I'm going to define complete tuple F of polyhedra in multi-octant. It is just collection of complete tuple of polyhedra at each coordinate octant. So we have many different octants of different dimension. In each octant, we fixed its own collection of polyhedra, and number of polyhedra in this collection has to be equal to dimension of such octant. So this was a multituple of polyhedra in multipositive octant. And now next definition. What is the local multiplicity of this multituple? Well, you have several tuples in several space. You have for each of them its own local non-symmetric covolume. Let us take all of them and consider their product. So local covolume of multituple is just product of multituples of all components. Okay, so this was a local covolume of multituple. But now it turns out that if we will, so we're interested in given collection of Newton polyhedra, given n tuple of Newton polyhedra. It turns out that for given n tuple of Newton polyhedra, one can associate certain collection of multituples. And local formula, which I'm going to describe in a few minutes, is as follows. We started with our given n tuple. We consider all possible multituples associated to it. I have to define what it is. For each of them, we have this definition, and we just sum up all these local terms. And we will get certain expression which is highly non-symmetric. Yeah. So first of all, we have for my given multituple, I'm going to associate few multituples containing different number of coordinate subspaces. So we have different number of k. K is number of these tuples. For k equal to 1, we will say that multituple is associated with our multituple only in one case, if it is original multituple. So our original tuple is a multituple associated with it. Let me define what multituple having two tuples we associate with given tuple. So let us define notion of admissible subspace for our original collection of polyhedra. Let us say that space R to G is admissible for given collection of polyhedra if exactly G polyhedra do intersect the subspace. So some of them are above the subspace, some intersected. So assume that number of subspaces, number of polyhedra which intersect the subspace is exactly equal to the dimension. It is first condition. And second condition is that our last polyhedron is in this collection. Again, you see that, well, maybe first term is very symmetric, second is not symmetric at all. So it depends on ordering of our system. So this is admissible system. Now let me assign a multi-tuple containing two terms for admissible system. First of all, admissible space. So first of all, if we have admissible space, we have, of course, corresponding decomposition of our space. We have, first of all, space Rg, R2G, we have complementary space, so we have this decomposition, and we have this projection. So just with any coordinate subspace, we have this decomposition and projection to the last component. Consider this case when our space L to G is admissible. Now I'm going to cook collection of polyhedra at each term. So first, how to cook collection of polyhedra as the first term as L to G, R to G. Well, we just have to take intersections of our polyhedra with our first space. By definition, there are exactly there are as many such polyhedra as dimension of the space. So we will get complete collection of polyhedra, and I consider it with induced ordering. So this was complete model G tuple as the first space. Model G tuple of the second space can be obtained in the following way. We just take projection of the remaining polyhedra under this map. They will form correct number of polyhedra in the complementary space. So with each admissible subspace, we cook tuple of polyhedra containing two tuples. Now this process can be continued. So assume that we are given complete tuple of polyhedra in the composition which contain n terms. And assume that last term has admissible subspace for its own collection of polyhedra. Then instead of this space, we can apply previous construction and split the subspace in two subspaces. And again, we will get full collection by that construction. We will get a complete F-tuple of polyhedra, which contains not m terms, but n plus 1 terms. Now definition. Multi-tuple of polyhedra is admissible is associated with our collection if it can be obtained by this inductive process. So if you can inductively obtain it by this process, then it is admissible, then it is associated with our tuple. Okay, and now we do the following thing. We just defined covolume of collection of polyhedra, assuming that this collection is Z0 is marked point for this collection. We will define it as the sum of these local terms for each full tuples of polyhedra related to our tuple. So this is the formula. Again, it is highly non-symmetric because when we construct each term, it is very important what is the ordering. Last polyhedron in each tuple has special role. So this formula is highly non-symmetric, but the following theorem holds. Assume that we are given any collection, any n-tuple of equations in C to the n, and assume that our system is generic with respect to this system. The question is, under what condition zero will be isolated solution, and what is its multiplicity? The answer is as follows. So solution will be isolated even only if zero is a marked orbit for our collection, meaning is that number of polyhedra which intersect any coordinate subspace of positive dimension k has to contain at least k. For at least k polyhedron, it has to be not empty. So this is first statement, and second statement is as follows. If this condition holds, then the answer multiplicity is just given by local formula which is just defined. Well, I would admit that this formula is really awful, and it is absolutely non-clear why, if I will consider polyhedra in different order, I will get the same answer. I don't have any geometric explanation of this event, but we know that this is by this theorem it is a multiplicity of the system, and multiplicity, of course, is not depending on ordering of systems, so it should be true. It has to be true. So this number is independent on the ordering of our system, and it is kind of local version of non-symmetric formula for mixed volume. It is kind of mixed co-volume, which is highly non-symmetric. And now I'm going to define another formula, which is much simpler, which is symmetric. So assume that we have, again, n equations and n unknowns in C to the n, and assume that zero is marked point for the Newton polyhedra. Well, first, I would like to consider another system which has much smaller degree. This system is as follows. Take any polynomial here. For this polynomial, we have its Newton diagram, which contains only few monomials from our polynomial. Most monomials are away from Newton diagram. Now let us do the following thing. Let us equal to zero all coefficients in monomials which are away from Newton diagram, and keep coefficients, original coefficients on monomials which are on this diagram. I will denote such polynomial p tilde. So consider our original system of equations and consider new system of equations, p tilde I are equal to zero, which has much smaller degree and which is much simpler. We just get rid of all monomials away from Newton diagrams. So first statement is that for these two systems, if they are generic with respect to the Newton polyhedra, multiplicity is the same. Well, I don't have kind of proof of the theorem which is not related with the previous one. By local formula, in fact, involve only these terms. So by local formula, we know that these two systems has to have the same multiplicity, but of course, this sounds very natural. Of course, of course, only terms which are Newton polyhedra are most important for us. So it's very likely this is true, and maybe very likely this corollary can be proven simply, but the only proof I know till now is based on this local formula. Now I'm going to further change our equation. Well, let us do the following thing. So we have collection of equations. And for each equation, it has its own degree. Again, we get rid of many monomials in our polynomial, so degree of our polynomial p tilde will be much smaller than degree of original polynomial, but still it has some degree, and we can consider product of these degrees. Let me denote it by n capital. Okay, now I am going to change my equations again. Instead of polynomials p tilde, I will consider new polynomial. To each polynomial p tilde, I will get the same term. And term is sum of coordinates raised to degree n, where n is product of those degrees. So we get new polynomials. And as you see, Newton polyhedra of this polynomial by construction intersect each coordinate subspace. Well, and now we have a following formula. So consider Newton polyhedra of such polynomials qi. So multiplicity at origin is equal to n, this huge n, which is a product of degree to degree n is dimension of our space, subtract mixed volume of Newton polyhedra of this auxiliary polynomials were constructed. So this formula, of course, is much simpler. And in fact, it is much, much more understandable. Let me even sketch proof of this result. So, you know, if you have system of equations, and if you will add to this system terms whose degree is bigger than multiplicity, you will not change multiplicity. This is always true. So by adding this term, it does not change multiplicity of our system at origin. Now this first term is nothing else but the number of solutions of the system in projective compactification. We just have n polynomials of the same degree in projective space. So number of solutions is equal to that number. But it turns out that all solutions of that system split in two parts. One part will be our original zero with its own multiplicity, and all other roots are roots away from zero. And the number one can check that for this number, Bernstein-Kostelenko theorem is applicable, so its number is equal to mixed volume multiplied by n factorial. So of course this formula is kind of much simpler, but maybe, you know, it involves huge numbers and huge polyhedra. And local formula kind of use only the smallest possible number of polyhedra which are involved in this situation. Yeah, so in fact, one can easily extend all these results to the case when you have sections of line bundles, invariant line bundles of a toric variety, assuming that these sections are regular sections of our line bundle, and they have given Newton polyhedra. There is one question which I don't know how to answer. I have no idea. This question is as follows. Well, maybe let me state it in the simplest possible case. Assume that on plane we have not two equations, but three equations, or maybe k equations where k is bigger than 2, and assume that they are generic with their Newton polyhedra. Still, we have a definition of multiplicity of solution. How to compute this multiplicity via Newton polyhedra. Of course, the answer for n equal to 1 is very simple. If you have any collection of equations, only the smallest order of equation is important. It will be the smallest order of, so the number will be smallest order of equation. But for n equal to 2, I have no idea how to answer this question. This is one question. Another one question, which also is kind of related to that, which I don't know the answer, on which I don't know the answer. And I think that this question is, this is a challenge to answer on this question. This question sounds really very important. It is as follows. Assume that we are given, say, collection of n equations, n analytic functions are equal to 0, say, at the origin in Cn. Consider subcollection of this in all n tuples of such equation. Consider subcollection of equations which has origin as a point of multiplicity k. What is the codimension of this number? Well, very natural question. And about, I don't know, 20 years ago, I asked this question to Arnold, and I was sure that he will give me a complete answer. But his answer was as follows. Well, I don't know. We really need this number. We need to estimate on this number. And we found such estimation with Andrei Gabrielov. With Andrei Gabrielov, we estimate somehow this codimension. Well, it's not so bad. It contains just extra logarithmic terms. But of course, this question is so important that maybe it's good to get rid of these logarithmic terms and to find explicit answer on this natural question. So this is one question which is very related to this story. And another question is just multiplicity of 0 for equations where number of equations is bigger than with generic Newton polyhedra, when number of polyhedra, number of equations is bigger than ambient dimension. That's it. Thank you.
Thank you very much. Are there any questions? Okay, if no, then let us thank the speaker again.